Today's lecture will be about different types of distributions and the distribution numbers. We're going to start by talking about a question we've already talked about earlier in the quarter. How many ways are there to rearrange the letters in the word Mississippi, the name Mississippi? Well, what I want to do is claim that the answer, whatever it is the same as the number of ways to distribute 11 balls into 4 boxes, with 1 ball in box 1, 2 in box 2, 4 in box 3, and 4 in box 4. We can see that by thinking of the boxes as the letters. Box 1 we identify with M, box 2 we can identify with P, box 3 we can identify with I, and box 4 with S. And then if we have 11 balls, and we'll think of the balls as the positions of the letters in the word. We have an 11-letter word, Mississippi. Here's position 1, position 2, position 3, position 4, position 5, 6, 7, 8, 9, 10, 11. And to get the word Mississippi, it would be like putting position 1 into the M box, putting position 2 into the I box, position 3 into the S box. And you could keep going like this for each of the different positions. Position 5 is an I, position 6 back to an S, position 7 an I again, positions 8 and 9 into the P box, etc. I won't put in the last two, but you can see what I'm doing. Any rearrangement of Mississippi would correspond to a distribution of these 11 positions, the numbers 1 through 11, into the 4 boxes in a different way, as long as we had 1 in box M, 2 in box P, 4 in box I, and 4 in box S. That would give us a rearrangement. So counting the number of rearrangements of the word is the same as counting these distributions. In other words, there's a one-to-one relationship between rearrangements of the word Mississippi and distributions of 11 balls into 4 boxes, as long as we have 1 ball in the first box, the M box, 2 in the second box, 3 in the third, and 3 in the fourth. I'm sorry, 4 in the third and 4 in the fourth. So the question becomes, how do we count these? How do we count the number of distributions where I'm telling you how many balls have to go into each box? Well, one way to do it is to talk about ordering the letters within each box. Let's look again at these boxes. Let's say we have the M, the P box, the I box, and the S box. We know that we're going to have, in a distribution that will give us 1 ball in the M box, 2 in the P, 4 in the I, and 4 in the S, that will represent a rearrangement of the word Mississippi. We know that there will be just position 1 in the M box. The P box gets positions, 9 and 10. The I box gets, what positions were in the I box? Let's just check. You have an I in the 2nd, 5th, 8th, and 11th position. And you have an S then in the 3rd, the 4th, the 6th, and the 7th position. So the distribution that takes the numbers from 1 through 11 and puts them in these 4 boxes looks like this. But let's just pretend that instead of just caring about which balls are in which boxes, it doesn't matter which order I write this 9 and 10 in. All that matters is that I have a 9 and a 10 here. Here I have the 2, 5, 8, and 11 in the particular order, but it doesn't matter. They could be in any order, and that would just mean I's in those positions. So if I'm imagine that order matters, I could write a distribution like this. 1, I could put a 10 in it. I could have 1 here, a 10 and a 9, an 11, an 8, a 2 and a 5, a 4, a 3, a 7, and a 6. And if I just told you number 1 goes here, number 10 and 9 go here in that order, number 11, 8, 2, and 5 go here in that order, numbers 4, 3, 7, and 6 go here in that order, that would really be creating the same distribution. I have the same balls going into the same boxes. How many ways are there to count these things which aren't distributions, but they're like strings of the numbers 1 through 11? I'm calling them strings of 1 through 11 because if I just write down the order 1, 9, 10, 2, 5, 8, 11, 3, 4, 6, 7, that's an ordered string from 1 to 11. Here I have 1, 10, 9, 11, 8, 2, 5, 4, 3, 7, 6. That's an ordered string from 1 to 11. There are 11 factorial ways to create an ordered, or I'll just say a string, which is ordered, from the numbers 1, 2, 3 through 11, where no element is repeated. But many of those represent the exact same distribution. For example, the 2 that I've written here. The one on top, if you just think of that list of 11 numbers as being a string, or the one underneath, that list of numbers being a different string. How many, for each distribution of the 11 balls into the 4 boxes, 1 in the first, 2 in the second, 4 in the third, and 4 in the fourth, how many different ordered strings would I get? Well, the 1 has to come first, but I have 2 different ways I can rearrange the 2 numbers that go into the P box. I have 4 factorial different ways I can rearrange the 4 that go in the I box. I have 4 factorial ways I can rearrange those in the S box. If I multiply those together, 2 factorial times 4 factorial times 4 factorial, and I'll put in the 1 factorial just to say how many ways I can rearrange that 1. This number is the number of ways I can rearrange the numbers within each box to create a different string that gives me the exact same distribution of the numbers into the 4 boxes. So of these 11 factorial ways to write down a string containing each of the numbers 1 through 11 once, I can group them in groups of size 2 factorial times 4 factorial times 4 factorial. Be clearer with that. Let me get rid of this. I can group them in groups this size, all of which will represent the exact same distribution. So to get the number of distributions, I'll only count 1 from each group, so I have to take 11 factorial and divide by this number of different ways to get that exact same distribution from different strings, and that will be 1 factorial times 2 factorial times 4 factorial times 4 factorial. This will be the number of distributions, and thus this will be the number of rearrangements of the letters in the word Mississippi. Now, a second way of seeing this exact same thing is to ask how I would create a distribution of the letters. How will I create a way to distribute the numbers from 1 through 11 into the box M, the box P, the box I, and the box S? And we've talked a little bit about this before, but let's go through this. I'm going to create a distribution by making a sequence of choices. And at each choice, I'll have a certain number of possibilities. Then we'll use the product rule to get the total number of ways I can make all of those choices. Remember, in order for this to be something I can use to count the number of distributions, each sequence of choices must correspond to exactly 1 distribution and vice versa. I can get any distribution through a sequence of choices. Well, what do I have to choose? I have to choose how many ways I can choose 1 of the numbers to put in box M. So I'll say choose how to fill the M box. Well, there are 11 elements, and I have to put 1 in there, so that will be 11, choose 1, or 11. Now, how many ways can I fill the P box once I've filled the M box? Well, there are only 10 elements left, and I need to put 2 of them in the P, so I'm going to have 10 choose 2, which is just, well, I don't want to simplify this too much, so let me write that as 10 factorial. No, that's 11 up there. 10 factorial over 2 factorial times 8 factorial. You'll see it'll be useful for us to leave it like that. How many ways can I fill the I box? Well, we only have 8 elements left, and I have to put 4 of them in I. So it'll be just 8 choose 4, which can be written as 8 factorial over 4 factorial times 4 factorial. And finally, how many ways can I choose to fill the S box? I only have 4 elements left, and I have to pick 4 of them to put in the S box. That will be just one way to do it, put them all in. So by the product rule, I can fill all the boxes in (11 choose 1 times 10 choose 2 times 8 choose 4 times 4 choose 4. And what is that here? That's 11 times 10 factorial over 2 factorial 8 factorial. Then 8 choose 4 will be 8 factorial over 4 factorial times 4 factorial. And then 4 choose 4, which we could write if we wanted as 4 factorial over 4 factorial times 0 factorial. I'll just write that there. And you'll see everything cancels. That, of course, is just 1. This 8 factorial cancels that 8 factorial, and we end up with 11. And I really could have written that 11 as 11 over 1 factorial. That gives me 11 factorial on the top. On the bottom, we have 1 factorial times 2 factorial. That 8 was canceled up there. 2 factorial times 4 factorial times 4 factorial. Exactly the same answer that we had above. Does this generalize? Of course it does. How many ways are there to distribute M balls into N boxes? So there are N boxes. If you tell me how many go into each box, M1 is the number going into box 1, M2 is the number going into box 2, M3 is the number going into box 3, etc., all the way up to M sub n, which is the number going into box n. And for this to make sense, we need M to be M1 plus M2 all the way up to M sub n. The total number of balls is the sum of the numbers that go into each box. Well, the answer, just generalizing the formula we had before, is M factorial over M1 factorial times M2 factorial through M sub n factorial. And that's a very important number, and we give it this name. It looks like a combination number symbol. Now we'll call it a distribution number symbol, or we'll also use the term multinomial coefficient. We'll explain that in the next video lecture. We call that this distribution number M on top, M1, M2 through Mn on the bottom. And remember, for this to even make sense, you don't want to write this symbol unless M is equal to M1 plus M2 all the way up to M sub n. So whenever you write a distribution number like this, the sum of the numbers below must equal the number on top. Now let me, without writing down every detail, tell you why this is the correct way to generalize things. If you go back to the first method, and we ask, what if we have M balls, or M numbers, and we distribute them into N boxes, with M1 here, M2 here, M3 here, M up to Mn at the end, you'll have M factorial ways to rearrange strings that contain each of those numbers exactly once. You'll have M1 factorial ways of rearranging them in box 1, M2 factorial ways of rearranging them in box 2, through M sub n factorial of rearranging them in box n. And thus, of the M factorial ways to rearrange the string of distinct elements 1 through M, you can group them in groups of size m1 factorial, m2 factorial through m sub n factorial, all of which will represent the same distribution, so that quotient will represent the total number of distributions. Another way, the second way we did that, is we just asked first to count the number of distributions. We said first ask how many ways you can fill box 1. Well, you have m balls, or think of them as the numbers 1 through m, and has to go, m1 of them have to go into that first box, so I'll have m choose m1 ways of filling it. How many ways can we fill box 2? We'll have m minus m1 balls left, and we have to choose m2 of them to go in box 2. How many ways can we fill box 3? We'll have m1 minus m2 minus m3 balls left, and m3 have to go into box 3. And that will keep going until the last box, when we'll have m sub n left. And remember, m sub n is m1. I'm sorry, I didn't write this properly. Let me state this again. For box 3, the number of balls we have left is m minus m1 minus m2. For box n, we'll have m minus m1 minus m2 all the way up to m sub n minus 1. That's the number of balls we'll have left, and I'll have to choose m sub n of them to go into the nth box. Notice that this number on top here is exactly m sub n, because when you take m and you subtract off all m1 through m sub n minus 1, you get exactly m sub n left. So this last combination symbol is always 1. And can we just multiply all these together? The answer is yes. The first combination number is m factorial over m1 factorial times m minus m1 factorial. The second combination number is m minus m1 factorial over m2 factorial times, you'll have m minus m1 minus m2. And then we'll keep going like that. The next one will be m minus m1 minus m2 factorial over m3 factorial. And then you'll have the top one minus the bottom, which is m minus m1 minus m2 minus m3 factorial. And we'll keep going all the way until this last one. And the last one is m minus m1 minus m2 through m sub n minus 1 factorial divided by m sub n factorial. And then here we'll have m minus m1 minus m2 all the way up to m sub n minus 1, and we subtract m sub n, so we go all the way up to m sub n factorial. Notice that this last one here will be 0 factorial. This one on top here will be m sub n factorial. So that whole thing at the end is just 1. What's really nice here, this will cancel this. This one cancels this one. This one cancels this up here. The last one here will cancel this one. And what we have at the end will be exactly m factorial on top. On the bottom, we'll have m1 factorial, m2 factorial from here, m3 factorial from here, all the way up to m sub n factorial from the last one. And remember, that's already 1, so we don't have to worry about it. And that's exactly our distribution number. So these distribution numbers, or multinomial coefficients, have a very simple formula. And it should be easy to remember, especially when you remember that this distribution number, m1, m2 on the bottom, is exactly the same then as our binomial coefficient or combination number, m choose m1. Why? The formulas are exactly the same. This first one is m factorial over m1 factorial, m2 factorial. Remember, here we have m1 plus m2 has to equal m in order for this to even make sense. On the right, we'll have m factorial over m1 factorial, m minus m1 factorial, but that's just equal to m2 factorial. This is m2 factorial. So these two are the same. And that should be pretty obvious from the a combinatorial perspective, because if I ask how many ways can I take m distinct balls and put them into two boxes, box 1 and box 2, with m1 in box 1 and m2 in box 2, here of course remember m1 plus m2 has to be m. So if I have m balls and I want to just distribute them m1 here and m2 there, how many ways can I do that? Well, I could say just fill up box 1. How many ways can we fill up box 1? M choose m1, and then box 2 gets all the rest. Well, how many ways can I do it? I can just use what we just showed about distribution numbers, and we showed that that's the distribution number m, m1, m2, like that. So these distribution numbers, in the simplest case, when there are only two numbers at the bottom, are just the combination numbers we were already familiar with. When you have more than two numbers at the bottom, they give us something new. Notice, of course, that we get the same thing if we have m choose m2. That combination number, that will be the same as m choose m1, precisely because m1 plus m2 equals m. Or combinatorially speaking, the number of distributions I can find just by counting how many ways I can choose the m2 balls to go into box 2. All the rest then have to go into box 1. So in the end, this is called standard problem number 12. Find the number of rearrangements of a word with m total letters of n distinct types and different letters. You could say that from an alphabet of size n, with m1 of letter 1, m2 of letter 2, etc., up to mn of letter n. How many ways are there to rearrange such a word? Well, the answer is the same as for the previous standard problem 11. It's this distribution number. So this distribution number counts rearrangements of m letter words that have m1 of the first letter, m2 of the second letter, through mn of the nth letter. It also counts the number of distributions. We often use this term, distributions of type m1, m2 through mn. That distribution number is created precisely to count that number of distributions.